not what they should be. They're terrible, and you know it. Excellent. So to clarify that, I generally say things that are somewhere between confusing and deeply and obviously incorrect. I'm not sure how many of which category are in here, but there's a bunch of all of that in here. It will just get worse unless you stand up and say something, so feel free to jump in. I think that is more useful than confusing all of us. So yeah, the title of the talk is All Our ML Ideas Are Bad and We Should Feel Bad. Why does it not love freedom? There we go. I do have this like Twitter, everybody's like all with the Twitter thing. I'll be honest, although I have a 3-letter Twitter handle, like I don't know what Twitter is for. I use it almost entirely for Yo support. So the Yo application is my primary messaging and communications platform. I'm not gonna tell you my user ID because then you'll all Yo me even though my phone's on silent. But if you look at my tweets, you're like, why is he always tweeting at this one guy about Yo being down? Yo's down a lot. It's not the most reliable service. But when it's up, it's amazing. And if you think it's a messaging platform, it's not. It is a distributed, participatory performance art project. So if you think of it that way, good. So quick intro. Here's the agenda. We're going to do basic questions. We're going to do a hopefully very, very short introduction to machine learning. It assumes nothing, and even by the end of it, you actually don't need to know any of it. So just look at the pretty pictures, it'll be fine. We'll talk about ML production, like why we think we want to use ML to do something about production. I think you think that. I definitely used to think that. A lot of people think that. I'm going to talk about, and that's the character of the ideas that I think are bad that we have. I'm going to try to identify if there might be, or the shape of what there might be some good ideas for using machine learning to manage or talk about or troubleshoot or do something with production. And then I'll queue up some future work for someone who is smarter and more ambitious than me. Cool. So basic questions, you know, the typical ones. Who am I? Who are you? Why are we here? We're going to try to hit the really big questions. We're going to do it in 32 minutes or less. So it might not be sort of, I've already heard Descartes mentioned here. It's not going to be some sort of Cartesian, profound conclusion about anything. But who am I? I'm a recovering systems and network engineer. I've been at Google for about 10 years. I've been working on machine learning for all of that time there. So this stuff seems, like I don't say that to be like, oh, like, you know, I was doing ML before ML was cool. But like, it doesn't seem like the new hotness to me. It just seems like an interesting way to solve some kinds of problems and a terrible way to solve other kinds of problems. And I'm hoping to convey that perspective to you to sort of counter some of the pretty phenomenal amount of hype that there is right now. I'm based in Pittsburgh, Pennsylvania. There's some other facts about me, but those are a few. Feel free to ask. Who are you? So there's some assumptions here, but who are you? Let me ask some questions. How many people in here have ever built a machine learning model on purpose in anger? That's like 7, 8 people. John Looney says he's one of them. He said John Looney only did it once and he'll never do it again. How many of you did it once and never want to have to do it again? That's another intro. Oh, that's seriously half the people who put up their hands the first time. OK, so the point that I should be taking, how many of you claim to be, get paid to be, or actually think of yourselves as data scientists? Yeah, because you all would see this and you're like, I'm not going to that talk. I'll learn nothing. OK, so no one in here actually knows any proper statistics, I'm guessing. Good, good. That way you won't call me on this. So the point of this talk is not for people who are machine learning experts, whether in infrastructure, algorithms, modeling. That's not the point. It is actually for you and for me. Why are we here? I mean, there are profound philosophical questions and answers here. Why are we here? We're here mostly to make our lives better. The point of you doing any of the talks that we're doing here, any of the learning that you're trying to do, any of the communication with other colleagues, you have some set of conditions in your life. Probably most of the conversations you will have here about your professional life, but I'm not judging. You can solve any kinds of problems you want. But most people are here to solve some sort of problem. So let's talk about those. Let's start with machine learning versus AI. How many people know the difference between machine learning versus AI? It's a trick question. Come on. All right. The difference between machine learning and AI, if it's written, you've all seen this tweet, right? Right? If it's written in Python, it's definitely machine learning. If it's written in PowerPoint, it's definitely AI. So this is a funny, like, oh, so delicious, right? So funny. There's a serious kernel of truth here, which is no one actually consistently uses the difference between these terms. So I'll make this differentiation, and then I'll tell you don't have to care about it. So turn your brains off for about 25 seconds. It's going to be great. So artificial intelligence is a family of technologies to try to make thinking machines. That should either fascinate you or terrify you, but as a production engineer of any stripe, it should make you incredibly skeptical. You should at this point wonder, yeah, how are we going to do that? How long is that going to take? How far will we actually get? What are the problems we're going to run into? And indeed, anybody who works on this is trying to answer all of those questions, and on very, very restrictive tasks, like, could you just drive a car? Like that, like it sounds both fascinating and also outrageously limited compared to the number of things people can do. Man, the computers. So in Pittsburgh, we have 4 autonomous vehicle car companies that start with the letter A testing their cars on the road. So we know a lot about all of these different algorithms, and they're okay. Like they're getting better, but they have trouble. They have trouble with snow, and they have trouble with the shapes of roads. They have trouble with intersections, but mostly they have trouble with other drivers. They're really actually good at cyclists and pedestrians, which makes me happy, but they're not always good at figuring out, like, well, now I can't, can I turn left? What is that other car doing? I'm just gonna stop in the middle of the intersection, which is a safe thing to do, but they do it all the time. So AI, it's gonna make thinking machines fine. Machine learning is a much, much more restrictive term and therefore much more useful in our context. It is a family or collection of techniques that enable computer algorithms to learn from data. That actually sounds pretty good, right? The making thinking machines part sounds like science fiction, which it is a little bit. This one sounds pretty good, so we're gonna talk about this one. This is actually potentially useful. Less useful than you would think it would be. But it turns out it looks like it might be useful. But it doesn't really matter because language is about communication, and guess what? People don't use these terms consistently, so you don't have to either. All right, so here's a very, very short primer on machine learning. Here we go. Everyone understanding everything so far? This is great. I mean, I haven't said very much, which you might feel like at the end of the talk as well. We'll see. So what the heck is machine learning for? Let us imagine you are a software developer and the task you have been given is, given a picture with fruit in it, tell me whether it's an apple or an orange. That's your task. So like, okay, cool. I'm going to take an image. I'm going to parse that image. And I'm going to figure it out. It's going to be good. So apples are red, right? Apples are red for sure. That's cool. And oranges are orange. So you're going to write an algorithm that if red, like do some pre-processing. Remember the pre-processing because it turns out to matter later. Not in this, but in almost everything else. But so, okay, you know, pre-process the thing, count the number of, find the things that are together. The things that are together, we call this object detection. Count the things that are together. Are they red? It's an apple. Cool. Are they orange? It's an orange. That was pretty easy. That was like a bunch of fancy crap and then an if statement. I can write if statements. I'm a software engineer. Look at me go. Right? Okay, cool. Wait. There's green apples. Okay, I mean, technically I knew that, but I hadn't thought about it because I had this like platonic ideal of an apple in my head, right? Looking at the image of the apple on the wall of the cave. There's going to be all kinds of philosophy references. You don't need to worry about them. So some apples are green. That's okay. So if red or green, then apple, and if orange, then orange. This isn't that bad. I mean, bugs happen in software, but now we've got it. Wait, what's that one doing? There's the thing down there, it's hanging out, and it's being green, and it looks kind of green, but I swear to God, that's an orange. I'm pretty sure it's an orange. It's a green orange. Those are a weird kind of orange, and they're yellow, and some of them are kind of green, too. Okay, so if it's red or green, it's an apple, and if it's orange or green or yellow, it's an orange. So we're gonna have some problems with the green ones already. We can see this is getting to be a little bit more complicated. Okay, and then they can be weird mixes of those colors. They can be bunched in together. Okay, look, oranges are bumpy and apples are smooth. So now I've got it, right? Screw all that other stuff, or maybe I remember that stuff, but I'm gonna go with bumpy and smooth. But now when we do the image processing, we notice that wet apples are gonna look bumpy to us because we're gonna check the edge. We're gonna like look at the edge of that, and we're gonna do, that's edge detection. It's gonna be magical. First we do object detection, then we find the transition between object and non-object, and we call that the edge. We look at it, and it looks bumpy. because our image processing isn't that sophisticated. You know what else is like multichromatic or modeled apples will also look bumpy to us because we'll have difficulty sort of projecting the map of the apple into the Z space, right? So we'll be like, okay, that might look bumpy too. All right, this is getting bad. So that's a green and bumpy apple. So now I don't even know. And then we go look, because we're just checking these by hand, because we were feeling pretty good about the bumpy thing. And we notice some of the oranges are smooth. All right, so now we've got, and then we're like, well, that one, okay, so that's yellow, which we thought, it's yellow and it's bumpy. It's about the right size. I didn't even talk about size, but we could try to do size. And I'm just a human, but I think that's a lemon. I don't think that's an apple or an orange. And it gets worse because sometimes people cut them open, and then you're like, and that one in the middle, so in English, lime, right? So that's a lime, which is different from a lemon in English. This is a fascinating distinction to me. But okay, so now what? This is unreasonable. So if you're the software engineer responding to this set of use cases, you've got a mess of, like, your code is junk at this point. And you don't, like, not that you ever like your code, but this code you're really gonna dislike because there's no sensible way to do this in a principled, decomposable way, because every time you try to get it and you're doing pretty well, someone's gonna walk in with an edge case and it's gonna mess up your code because your code will need to be refactored in response to an example that you're not correctly categorizing. Okay. So that's where we got. So we need a better approach, and this is really what machine learning is. So machine learning, we need a bunch of, these words are gonna matter, labeled examples. So a label is just a name. But what you will find is the machine learning people who are really good at it, that's not me, I know some people like that, I barely understand them. But the ones who are really good at this use a very specialized jargon in order to communicate sort of group membership, in order to communicate status. It's a status-seeking thing. I mean, they say it's to communicate details about models, which maybe it is. I don't understand that part. In the same way that, like, in Unix, in the Unix community, we have like a bunch of intentional, foolish mispronunciations of words in order to gauge people's membership in the Unix community. So if you ever meet someone who says like /etc, you know they don't know anyone who knows anything about Unix, and if they know anything, it's all self-learned because they've never heard someone say etc before, which is weird, right? Similarly, in New Mexico, they actually call the editor vi, which I thought was odd. And I think 6 would be a better name for it. So we need a bunch of labeled examples. So a label's just a name. It's a name that describes membership in a category in this case. And an example is something that is characteristic of what you are trying to process. In this case, the concrete task we can think about is predicting or categorizing. And those actually, I'm not going to explain why, but prediction and categorization are essentially the same task. There's ways to think about it, which is one or the other. So a labeled example. Sounds good. OK. We need some system for updating some kind of data structure in response to examples. And then we need a cost function to tell us how bad our model currently is. The model is just the map of predictions. The map of predictions you can think of as what we think we know. And the cost model is a way to tell us when we're done, when it's good enough. So the things that we look at are called features. So when I said color is a feature. Smoothness or texture is a feature. Okay, that sounds pretty good. And you can imagine if you ever hear someone doing feature engineering, most of that is just meaning humans trying to figure out what's predictive of the thing they're trying to do, which humans do all the time. You're like, I think time of day is important to figuring out whether we're going to run out of capacity on Tuesday. You're like, yeah, I think so too, because every single morning the traffic goes up, and I think time of day is probably predictive of traffic in your environment, for example. Cost function is just an evaluation of that. So the things we're processing are called features. The place that we're storing the state about what we think we're doing depends on how you're storing it, but it's either called a map or a graph. There are a ton of different ways of doing this. Don't worry about it. You can feel free to take, like, the Coursera course on machine learning has a fair bit of math, but it's not too bad. It'll teach you stochastic gradient descent, which is just sort of walking through a space mathematically and figuring out a point that probably is a good point on the graph, but not necessarily guaranteed to be a good point on the graph. But in any case, we're not going to talk about that versus deep learning versus other approaches. It actually doesn't matter for purposes of this talk. OK, so at this point in the talk, one of two things is true, possibly both. Everyone in here understands quite a lot about machine learning and what it's like, how it works. And the second is you've all been stunned into submission. Stunned? Stunned. Good. Good. OK. No questions so far then? Seriously? All right, here we go. It's your funeral. OK, so what is this ML thing for? And let's like scope it. What SRE kind of a thing would we want to use ML for? Like, what should we do with it? Well, I can think of, like, generally what I would say is, what do you do any automation? What do you automate, right? You automate the kind of stuff you're unwilling to do over and over and over again. Now, you can think of machine learning as being sort of a more sophisticated, more flexible form of automation. So you're like, well, if I do this task over and over and over again, I will automate it in a templated way. But there's lots of things that none of us have automated because we can't figure out how to template it. We would like, I could automate that. In order to automate that, I need to know whether it's a this or a this. And if it's this, I need to figure out whether it's this one or this one or this one. But wait, but if it's one of our Asian data centers, then we would have to do this other thing, but only if it also has the stack from the developers in Haifa who have this other set of, right? So now like you've gone tired and frustrated just thinking about the automation, and you're not even sure how to get started. So machine learning, right? So let's talk about specifically monitoring maintenance. How many people, so you get paged, how many people have monitoring with 100% fidelity so that you have 0 false positives and 0 false negatives? Yes, yes, right there. Amy Rich raises her hand, ladies and gentlemen. That was hilarious. Seriously, like, so what do you do? What do you do if you get a page that's bogus? You're like, it's not, like you see it, you look at it, you're like, that was just the wrong page. Like it just wasn't, you didn't need to be paged then. What do you do? Like, okay, so that's a bad answer. Like, so wait 5 minutes is a bad answer, not because it won't go away, because it's gonna page your colleague tomorrow and they, with every right, will be mad at you for not doing something. What you ought to do is say like, hey, is there some systematic way to change this alert in order to not page people unnecessarily? Where in this case, people was you, but using the broader sense of empathy, people could have been someone else, right? So be nice to other people. Okay, so fine. So you change the threshold. You're like, actually, let's add a hold down timer to that because sometimes this is a noisy alert, and let's wait until it's at least been bad for 10 minutes. That's a fine thing to do. Or let's wait, it said threshold was 82, but really we should set the threshold to 84 because that's what makes sense. So a lot of us do these sort of tweaks to the thresholding. It's tedious, it's annoying, and as soon as you have 800 or 10,000 or 100,000 alerts, it really gets to be a full-time job just tweaking thresholds. And later, one of your colleagues is gonna come along and say like, hey, do you know why this is 80? And you're like, I mean, it's 80 because it's 80. And you're like, well, I looked at the commit history and you set it to 80 2.25 years ago at 3 a.m. And you're like, well, I probably got paged when it was 78, so I set it to 80. That's not a good reason for it to be 80, but if that's your reason, you should let a computer set it to 80 because they don't, like, you didn't have a good reason, it shouldn't have a good reason either, right? So that's one idea. Alert suppression and analysis. So not just like changing thresholds, but finding and suppressing false positive alerts and doing signal analysis on those. Okay, capacity planning prediction, right? Do we have enough capacity for foo under bar conditions? Sounds good, right? Validation of canaries, can we stop bad pushes? Root cause analysis, this one's my favorite, like root cause analysis, people are like, I will tell you why you're getting paged. There's a vendor downstairs who's going to tell you why you're getting paged with high confidence across multiple different kinds of monitoring streams. It's going to be great. Automatic service and resource scaling. So if you have a pool of extra resources, but you're not using them to save money, when should you deploy them? And if you've ever had to like log into some control plane and add capacity to the service because of the use of the service, it'd be nice if the computer would just do that for you. So we can think of, these all sound, some of these sound compelling to someone in here. There's got to be someone who finds one of these ideas compelling.
Did you take these off of marketing brochures?
I did not take these off of marketing brochures, although if this SRE thing doesn't work out for me, no, the marketing people won't hire me. Okay, so what's wrong with any of this? This sounds great. It sounds lovely. It sounds grand, if we can be culturally appropriate for a moment. So seriously, why shouldn't we want the computers to do these things? And like my answer is no, these are actually great things to want. There's no reason not to want these, except that most of these particular ones you probably can't actually have. So it's like when you were a kid, like the thing that you wanted, but you could, I mean, maybe you all grew up rich, but I wanted a lot of stuff I couldn't have. It was not bad for me to want it. It just didn't really have any relationship to whether I was gonna get it or not, and this is the case here. So let's talk about one idea, categorizing and prioritizing tickets. People talk about this one. Okay, so you have some system that lets work, tasks, items come into a work stream of a team of people who works on production engineering of some kind. Those tickets, we can call them tickets. Different people call them different things, but let's call them for purposes of here tickets, because I have a picture of a thing with tickets, so we're gonna call it a ticket. See how that works? It's a circular definition, goes round and round. So tickets, right here, they might be generated by people. They might be generated by computers. Cool, sounds good. The problem is, you got a lot of them. So just tell me which ones actually matter. So here's the thinking. Here's the general idea. You want to focus the work of your team. So the first thing you do need to do is you need to get the work of your team in a place. It sounds really basic. Many things that are profoundly true and super useful sound really dumb when you first hear them. It's not a dumb idea, it's just kind of an obvious idea that most of us don't really do. But take all the work and put it in a place. So you take all the tickets and you put them in a single ticket queue going because you don't want to have to check lots and lots of ticket queues. Okay, sounds good. This is like Molly's talk of take all the monitoring things and put them in a different monitoring thing so you can look at that monitoring thing. It's actually a super sound idea. Okay, cool. Humans and computers together create too many tickets. Especially if you have any sort of automated ticketing, like subcritical alerting that says like, hey, before next month, you really have to do this thing. If you have computers that do that, you definitely are gonna end up with too many tickets, and many people have systems like this. So now you're spending all your team's time doing metadata work about the work. So you're prioritizing, canceling, responding to, bulk editing tickets. If you've ever bulk edited a collection of tickets to say like, will not fix, obsolete, all in a different category, return to sender, void where prohibited. If you've ever had to do any of those things, you got too many tickets, because now you're wasting time managing tickets instead of doing the work that the tickets were supposed to represent. So we will use machine magic, and then things will get better, which is what we want. Sounds good. Okay. So here's gonna be the algorithm. We're gonna determine those, remember the features? We need some features, like what are the characteristics of a ticket? Could be who sent it, what it's about, the words in the ticket. Like, I don't really know. I mean, I could guess. You all could guess. You can probably guess better than I do. But we've got some idea of like which parts of the ticket might tell us bogus ticket, good ticket. Waste of my time, super important. Like we need, and we don't have to, it doesn't have to be a binary categorization. We'll probably bucket it. It'll probably be like completely useless, totally ignorable. I guess I should look at sometime. Oh my God, look at this now because it's gonna wake you up in 4 hours, right? So maybe there's some spectrum of that. Okay, fine. And by the way all the smart kids are doing this thing called feature engineering now is they're using computers to do the feature engineering for them. So it's algorithms all the way down, and all of us are completely extraneous at some point in the near future. Just hold on, it's gonna be great. Okay, so we get labels from existing tickets. We look at, like I would look at them by hand and look at them. We're gonna look at the final priority of the ticket as being associated with the priority, like if you have some priority scheme that matches importance, okay, good. If it's closed, like will not fix, obsolete, useless, then you're like, that's a pretty good signal that like nobody needed to work on this. There also might be a signal like sat around for like 20 months. That might be a like, well, if it sat around, it probably wasn't that useful. Although there's some false positive and false negative in both of those. Closed fixed, especially if somebody interacted with it. But anyway, we're starting to imagine, right? You can sort of feel, this feels like we could train a model on this. We're gonna train a supervised learning model. Don't worry about what supervised learning is, but if you care, like it's not that challenging to figure out. We're gonna use the model to set the inbound priority for tickets, and things are gonna be great. Okay, cool. Ticket bliss, all the tickets are gonna have the correct priority automatically set, including some of them just being automatically rejected. Does this sound good? Like, sounds good to me. Does this sound good? Does anybody buy this? This is a terrible idea. All right, so wait, there's a joke now. So there's one joke in here. The rest of them are actually just me, sorry. So a machine learning algorithm walks into a bar. The bartender says, what'll you have? Machine learning algorithm looks around and it says, I'll have what everyone else is having. And promptly orders a coaster, right? So what's what's stellar about that joke is that that is exactly the kind of thing that algorithms do, by the way, right? Like, it is, every single person in that bar has a coaster. That's what they ordered, right? It's the kind of misunderstanding computers do. Okay, so what is wrong with this? It's not so much what's wrong with this, it's how you could have avoided doing something this complex. Like, so there's a way better way to fix this problem, which is generate massively fewer tickets, right? That was a solution that was within your grasp before I came in and talked about apples and oranges. You didn't need me to show you pictures of apples and oranges and how hard it is to categorize them, to have some straightforward approaches to massively reducing the inbound volume of tickets, if that's your problem. If most tickets are being ignored and going unworked on, then you're actually not going to have any signal about which tickets are really important for the reasons, right? So first of all, if we're bored and overworked and frustrated, we actually tend to do more random work. We do this like seeking out behavior. We're like, oh, I'm kind of frustrated. I don't know. Like if you've ever done this, like so much to do, I'm just going to do this thing. Well, now if I'm using your actions to decide what was important, I've got an overworked engineer who's just doing semi-random work because they're tired and they've got learned helplessness, and they're just doing something to avoid doing nothing, but they're pretty sure they can't get ahead of it. That's a terrible signal. All right, so now we don't know what's important, but that's okay because we're also not doing important things that are in the queue. So we also don't know what's not important because there's important things we're not working on, there's unimportant things we are working on, we don't really know. So those are two problems. Third problem, there's not enough examples. There's not even close to enough examples. So there's somewhere between 10K and 100K examples. Sounds like a lot. It's a lot to look at for a person. It's not even close to enough for a machine learning algorithm. And there's definitely not enough properly labeled examples. Like if you really go down to it, you will struggle to produce 1,000 tickets that are correctly labeled. And again, like imagine the amount of work it would take to label 1,000 tickets, and then let me tell you, you're not even close. So that's bad. Okay, so then the next thing is, you gotta pay attention to those. Those are coming back. Okay, automatic root cause analysis. This is gonna be great. This one is gonna be great. It's not gonna be great. This is gonna be great. Okay, so the general idea, outages are difficult to troubleshoot. So many things can contribute. Outages last too long. Given an alert or an outage or an incident, given a bad thing that happened, tell me what caused it. Use the machine magic and profit. It's going to be great. Okay. So what's wrong with that? Well, there might be a better way to fix this, which is when most people who talk about using machine learning for root cause analysis, what they're actually doing is some combination of correlation and other straightforward statistical techniques. Now, the only thing wrong with using correlation and some kind of regular standard statistical correlative techniques, literally the only thing wrong with that is you cannot get venture capital funding to do that. That is literally the only thing wrong with it. So use that, like unless you are trying, if you are trying to get venture capital funding, I have a different talk to give you. But if you're not, if you're trying to solve your problems, statistics is your friend, and you actually don't need very many of them to do most of your job quite well. So again, there are going to be a couple things, and we'll talk about that in a second. So again, not enough examples, insufficient information about accuracy, and way too few labeled examples. Unless you are unlucky, you do not have 100 million outages per year. You have, I mean, I don't know your network.
Your mileage may vary.
Your mileage may vary. I do not have oh God. Anyway, not enough labeled examples. Good. Okay, this one is definitely going to work. Machine learning, canarying, push some code. Sometimes it's bad. This is shocking, right? We have some software. We have joined the CI/CD religion. We are novitiates, so we're not good at it, but we really are true believers in it. We push our new software all the time, like every day, every second if we could. We push it every single time anybody changes anything. We're going to push new code to production. It's going to be great. Continuous integration. For some reason, our software is not perfect all the time. We're working on that. We're confused about that, but we've noticed it is not perfect sometimes, okay? So we're going to write tests, and the tests are going to fire, and it's going to be great. Okay, we're going to use machine magic to tell us when the tests are going to be done. What, if anything, is wrong with this? Okay, first of all, there might be a better way to fix this. So again, if we add more tests, which is tedious, it is tedious to add tests. But actually, if you go back and look at the general idea, we needed the tests for the signal anyway. So you can't get around with writing the tests. You might even write more tests. So you're going to solve a big chunk of the problem just by adding more integration and functional tests. Okay? There's a low certainty, this one is interesting to me. There's a low certainty of which pushes are actually bad and what the event horizon of your knowledge related to that is. So you do a push, 8 a.m. on a Tuesday. You could discover at 5 p.m. the subsequent Wednesday that that was not a stellar push, that there was actually kind of a subtle but really important problem with that push, and now you got to go clean up after it. Does this happen? Anybody had anything vaguely like this happen where there was a delay? All right, I see some hands, right? So this could happen. Okay. Well, what happens to the model that you trained where you said that push was good? You knew that push was good because you didn't take any alerts and customers didn't, whatever you were training your model on. So now you have a model that's positive that was a good push. You're going to push some more. So now you got to roll back your model to like what happened before. You got to inject new data. You got to train it. So the uncertainty, not only about which pushes are truly good, but when you know that is pretty profound. You don't have enough examples. You might have 100 pushes per year. You might have 10, 1,000. If you are pushing like dozens of times a day, you still have order 10 or order 100,000 pushes. You're not even close to enough data, and labeling those data with high confidence again. All right, so I know it's getting tedious. This is what you do when you're trying to slap together a presentation. You want to duplicate slides. It makes it last longer. We're stretching it out. No, that's serious. This is serious content. It's important. Okay, so most of it, as I said, most of what people call machine learning in the industry is actually marketing ML. So when you talk to the sales engineers and you read the brochures, it's definitely deep learning. And they will always say deep learning because everything's got to be deep learning or you can't get the venture capital. It's very important. But in reality, you talk to the people and they're like, I mean, we do have a model, but we don't use it for a lot because it doesn't have great accuracy and it's kind of expensive to retrain. So we use a lot of correlation techniques and a bunch of clustering. I'm like, oh, so you use like k-means and some correlation tests. That's what you're doing? That's pretty good. It is good. So there is some math, but you should use as little math as necessary. I don't dislike math. I'm just saying you shouldn't borrow trouble by getting extra math. Okay, so by this point in the presentation, you should be thoroughly depressed or thrilled. You should be thrilled that the marketing is bogus, because as engineers, we're like, I love it when the marketing is actually wrong, because I always suspect it's all wrong. It's great when somebody tells me this confirmation bias. Everywhere I look, I find more confirmation bias. It's interesting. Okay, so let me tell you just a couple, because we're short on time, plausible production uses of machine learning. It's not useless. Okay, here's one plausible use, right? So what is the requirement for plausible use? It needs to be something that can be clustered, categorized, or predicted. Okay, you need loads of data, truly phenomenal amounts of data. You will not believe how vastly, hugely, mind-boggling much data you need, right? Long way down the road to the chemist. Anyway, you know this quote, but it's going to be good. You need to be thinking about hundreds of millions of data points, thousands to millions of labeled examples, and you need to have some idea of what part is predictive. So here's your most important pre-work. Put your data in a place and know what it is. All your data, seriously, data, data, data. If you don't have all the data that you think you might need in a place, there's no point in even starting this journey. So what I recommend most of you, including most of us, do now is figure out what kinds of problems you might want to solve, gather, put your data in a place, and learn something about the uses and limits of machine learning algorithms. So future work. As I said, this is future work for someone much more clever and more ambitious than me. So someone could be in the audience who could do this. It seems like this is useful stuff to do. I just don't want to do it. It just seems like hassle. So I think we need an ontology of machine learning for production, which is what there is. What are the objects and what are the categories that we're working on? I think we need an epistemology, which is what are the data that we know and what are the data that we need to know in order to make substantive use of these predictions in our infrastructure. And then we need the metaphysics. I mean, nobody actually needs metaphysics, but you probably do need the metaphysics, which is how are we going to apply those two together? So this is a cute kitten, and the point of the cute kitten is to distract you from asking questions. Do you see that kitten? It's a very cute kitten. All right, thank you.
Okay, so I couldn't challenge anybody to come up to the microphone stand, but can I get any hands that I can run a microphone to you? Ah, good, one brave soul.
So I'm surprised you didn't get onto this when you were talking about looking for root cause analysis, but you seem to be saying that machine learning does a lot of correlation, and you're complaining that you can't make causes from that. So isn't it a sort of crime to say correlation and causality are related? So you can correlate swimming pool deaths with Nicolas Cage films, and there's a correlation,
Is that true?
but it's not cause.
Is that
so
true?
How do you address that question of causality and correlation?
I love the fact that I gave a talk littered with philosophy references and I got the demonstrate causality correlation problem. Yeah, so I think in reality, it's a kind of profound problem. At its most material form in our lives, all we have is correlation barring very, very careful human analysis. And so one thing that I have seen, and this requires an enormous amount of metadata management that I haven't seen people do very systematically, is tagging and structured data in your postmortem archive. So if you are writing careful human analyses of outages, it will be possible to actually extract true causes from those, because at this point, all we know how to do is correlate things and then process those through human brains to derive plausible causation. So that's a weak example, but that's what I would say to that.
Hold on, Laura.
Yep. Okay.
So there are all these cool tools out there, like TensorFlow and stuff. And the practical approaches tend to be things like simple statistics. Do those tools still help us at all to scale out these problems?
They can. So what I would say is the way I think about this as an infrastructure or systems engineer is I think with those tools, you are borrowing an enormous amount of complexity, so you better have a plan for getting a lot of value out of it. Now, you can get a lot of value. It's a little bit hypocritical of me to give this entire talk because Google obviously uses a ton of artificial intelligence, and I run machine learning at Google, and I can tell you we're making a massive investment in it, but we also have a massive amount of data, and we try to only apply to the problems that we actually have a massive amount of data about. So I would say, maybe. It might be worth it, but you would have to do that analysis. TensorFlow is fine to play with. Yeah, Laura.
I'm really glad to see this talk because I seem to remember saying a lot of this to you 4 years ago, so I told you so, haha.
All right, this is a talk by Laura Nolan, ladies and gentlemen. Laura Nolan gave this talk. Thank you, Laura. It was a truly excellent talk. I like your cat.
I like the cat too. So I think another problem that might exist for ML and AI usage in production systems is that you launch a new thing and system behavior can change quite radically, and that might invalidate an awful lot of training that you had done on a previous model, even if you could find enough labeled examples and blah, blah, blah. So I think do you think that's a problem as well?
Yeah, so there's actually two kinds of problems that you just highlighted there. One is reality changes substantively such that your model no longer represents reality. A closely related problem is your data about reality changes in a biased way. So the easiest way I know how to explain this is imagine you have a model of user behavior on a website that has some sort of geographical, cultural, or linguistic component, right? So something like people in one part of the world tend to do A, but people in a different part of the world tend to do B. There's nothing wrong with A or B. It's just people do different things. Language is a good way. There's lots of human languages, and people use different ones in different parts of the world predominantly. If 6% of your data were from South America, and you lost all data from South America for 5 days, you might not notice, because in aggregate, that might be below your threshold. Remember those monitoring thresholds? Someone on your team is like, 6% is not worth alerting over. Forget it, screw it, moving on, right? So somebody did that. So now you haven't had any data from South America for 6 days, 7 days, 8 days. You're training machine learning models. They are now crap. They are terrible at predicting anything in Spanish and anything in Latin America. Now they think all Spanish speakers are in Spain, which is demonstrably untrue, right? And the second is they don't know anything about all of Latin America, so they also have weird predictions for Portuguese. So the machine learning model is now accurately predicting based on what it knows. So both of those are really significant problems, and both of them have expensive solutions. Yep.
Okay.
Yep.
So thank you. Please thank Todd.
Cheers.